In this class, we will discuss about the dual phase simplex method, that is another method to solve LPP linear program problems. Dual simplex method. And before getting into that method and solving a LPP, you should know what I mean by dual of a LPP. So duality, we have duality. Okay, associated with every LPP, you can define there is another problem called the dual problem, dual of LPP, dual, dual of a linear programming of LPP. Associated with every LPP, you can define another problem that is known as dual of LPP. And the original LPP is called the primal problem. The original LPP is known as the primal problem. Okay, primal problem and dual. Primal problem and dual. Now let the primal problem is in the canonical form. The canonical form, the canonical form of a primal problem. That means the LPP to which we are defining the duality. Dual, uh, we call it as primal problem. So it is, let it be maximize. Maximize z is equal to, this is canonical form, standard form. So z is equal to, we are using the arbitrary notations. So z is equal to c1 x1 plus c2 x2 plus etc. plus cn xn. C1 where C1, C2, C3 etc. Cn are the our course coefficients, and subject to the constraints, we have a11 x1 plus a12 x2 plus etc. plus axn, and its canonical form is, if maximization comes, for maximization we have the canonical form all less than or equal to v1. So the, and etc. we can say it, the a11 advances like this, a12, a13 etc. A21, actually in the next row you will get a21 x1, a22 x2 etc. a2n xn, and like that you will get am1 x1 plus am2 x2 plus etc. plus am xn less than or equal to em. And for this is for every xi greater than or equal to 0. Okay, and this is our canonical form of maximization, and the dual of this problem is defined as the dual of the above is defined as minimize z star, minimize So maximization problem becomes minimization. So minimize z, that is z became z star is equal to then b1, b2, b3, etc. bm. That means our right hand constants. Right hand constants we are talking about, that is uh, given as the coefficients, the cost coefficients. So b1, and we are introducing two variables instead of x1, x2, x3, which are the decision variables. Here we are introducing w1, w1, w2, w3, etc. as the decision variable. So b1 w1 plus b2 w2 plus etc. plus I will get bm wm, bm wm, bm, bmw. So subject to subject subject to the dual constraints, that is nothing but you have again the decision variables w1, w2, w3. So you have to write the constraints in terms of that w1, w2, etc. wm, and the coefficients a11, a12, a13, a21, like that. That will not change. So we'll get it as a11 w1 plus a12 w2 plus etc. plus a1 a1n, right? a1n wn, a1n w uh, w wm, sorry, a11 w1 plus a2 plus etc. a12 a1. Okay, a1 a11 w1 plus a, not a12, actually it is a21 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 w2 plus, that means your this is your n, uh, your a11 a12 a13 a a13 x3 plus etc. So this is the row, right? So the row now it is happen you can write this a11 a12 a13 row elements, row entries as columns, column elements, and the column corresponding to our primal problem coefficients is, that means a, here it is, you have a21 x1 plus a22 x2 plus etc. plus a2n xn is then equal to b2, right? So this a11 a21 then next a31 like etc. that we will write, which we have written as column, we will write as row in this case, row. So a11 a21, then you will get a31 w3 plus etc. Then finally you will get a how many rows, am, right? M rows. So m am am am1 and wm, right? And the less than or equal to sign becomes greater than or equal. That means our this maximization problem became minimization. Max z is equal to in z star, and your less than or equal to sign became greater than or equal. So greater than or equal to, and the constant, right hand constant, now it is you can swap that with our cost coefficients, that is c1 c2 c3 etc. So here it is c1, right? Yes. C1. So similarly, we have A11. So we have the next is your A12. A12 W1 plus A. Then second row, that means your second column. So A12 and A22. A22 W2 plus A31 becomes A32. A32. Like A32 W3 plus etc. plus AM2 WM and greater than or equal to C2, the second host coefficient, right? And so in that manner you can write all the dual functions. Okay, and we will at last we have A1n W1 plus A, right? 2n W2 plus A, 3n, right? W3 plus etc. plus A mn Wm greater than or equal to C, and our decision variables, earlier it was x1 xi general, we have here wi wi greater than or equal to 4, where I varies from 1 2 3 etc. up to m, right? Yes, not n is m, right? Now yes. So this is our dual of LPP. Now we will try to solve some problems. So example problems are examples. First example is construct the dual construct dual of the following of following. So it is given as the primal problem given as max z is equal to 3x1 3x1 plus 5x2. Okay, subject to constraints 2x1 plus 6x2 then or equal to 2, and we have 3x1 plus 2x then or equal to 35, and 5x1 plus 3x2 less than or equal to 10, then x2 then or equal to 20, then x1 x2 then or equal to 0. So if you compare this with our standard form, standard canonical form, that is nothing but this, yes, the canonical form of a primal problem. That means you have the maximization problem. Here also the example, the examiner has asked you to find out the dual in which max set is there. So no problem, you can follow this canonical form, that is max set. And max set, its canonical form, it is the constraints are the linear inequality constraints are less than or equal to time, right? So if it is not, you have to make it less than or equal. Okay. In this case we have I think is the constraints are less than or equal to less than or equal to less than or equal to, right? So it is in the standard canonical form, and also xi x1 x2 is greater than or equal to 0 also. So it is in, you can conclude that it is in the canonical. right? So here we will find out the dual of this, that is dual of max z will be your minimization. Maximization problem becomes minimization, and z is z star is just a notation. Okay, z star that's equal to, you will get b1 b2 etc. You have to introduce the new decision variables, that is w1 w2 w3. Here the decision variables are x1 x2, so we have yes x1 x2, but there should be m number of, that's how many constants, right hand constants are there, so that many number of decision variables you have to define. That means 1 2 3 4, right? 4 constraints are there, 4 right hand constants are there. So w1 w2 w3, w1 okay, w2, then w3, then w, right? 1 2 3 4 is 4 decision variables you have to declare, and the coefficients is in dual, the coefficients are b1 b2 etc bn, right? So b1 is, this is b1, b1, and this is b2, this is b3, b4. So 50 w1, 35 w2, right? 35 w2, then have 10 w3, then 20 w. So this is our minimization problem. So, and this is subject to the constraints. So the constraints looks like in dual, have the constraints like your c1, c2 etc. The post coefficients, right? So subject to the constraints and the system variables, we have the less than or equal to, or less than or equal to becomes, yes, if you observe this, yes, all less than or equal to became greater than or, right? Greater than, so greater here also, here also, and a11 a21 etc. That means a11 a12 a13, that a matrix, okay, a matrix you have to, in a matrix uh, earlier row you have to write it as column. In a matrix you have row, that row you have to write it as column. That means, and w1 w2 etc wm, that means up to w4. That means we have this, yes, a matrix a is equal to, we have 2, right? 6, then 3 2, right? 3 2, and then we have a 5 x1 coefficient 5, next to coefficient 3, right? Then in the last case we have x1 coefficient 0 and x2 coefficient 1. This was our matrix A, and now in this case we have 2 6 row, we will write as column, right? So that means we have this column elements 2 3 5 as 2 w1 plus 3 w2 plus 5 w3 plus 0 w4, and less than or equal to becomes greater than or equal to c1 c2 c3. That means earlier our max problem we have c1 is 3 and c2 is 5. C1 is equal to 3, c2 is 5. So this is greater than or equal to 3. Then similarly we have 6 w1 plus 2 w2 plus 3WP plus 1W4 less than or equal to becomes greater than or equal to and is 5. Right. So and Wi is same like our xi apply greater than or equal to 0. Right. So this is our dual of the given problem. Now we are moving to the next example problem. Example 2, we have maximize z equal to the LPP 3x1 plus 7x2 plus 9x3 subject to the constraints x1 minus x2 plus x3 greater than or equal to 5 and minus 3x1 plus 2x2 less than or equal to have x1 x2 x3 greater than or equal to 0. That means non-negative. So this, if you observe this problem, primal LPP, you will find that this is not in our canonical form. That means for max said we have the less than the constraints must be in less than or equal to inequality constraint less than or equal to or. So the first step is to make it in canonical form. Okay, canonical force canonical form is max set max then 3x1 plus 7x2 plus 9x3 subject to the constraint is multiplying this by minus 1. So this greater than or equal to looks like that. So minus x1 plus x2 minus x2 less than or equal. Now all the other are same, like minus 3 x1 plus x2 less than or equal. And also we have x1 x2 x1 x2 x3 greater than or equal to 0. So this is our canonical. Then you apply the dual conditions, right? Dual operation. So max set becomes min set. Maximization problem becomes minimization problem. So minimization of z star, okay, equal to you will get it as yes. Once you find out the matrix A, let us find out that there is matrix A will be 0. That is 1 and this is 1. Then we have 3, 1, 2 and 0. So to take the transpose, so A transpose will be A matrix in minimization. And you have the constants is minus 3 and 1, right? Minus 3 and 1, and we are defining this minimization problem as 3W1 plus W. Right, so how many number of constraints? 2 number of constraints. So the number of constraints equal to the number of decision variable in the dual. Number of constraint equal to number of W's or number of decision variables in the dual problem. Right. So minus 3w1 w2. So we have two constraints. So two w. If I have to declare two variables w1 and w2. Right. And the subject to the constraints in the dual becomes your air transpose. That should be having this minus 1 is 3. That means minus 3w. Right. So and less than or equal to becomes greater than or equal to, and the cost coefficient. That means is for x1 it was 3. Right. 3. Then minus w1. Then the next column you take 1 and 2. So that can be written as raw. So 1 into w1 plus 2 into w2. That will be greater than or equal to less than greater than or then greater than or equal to the x2 coefficient, that is c2, that is equal to 7. And finally we have the last thing, that is minus 1 0, last column. That can be the coefficient of w1 and w2. So you write it as rho. So minus 1 into w1 plus 0 w2. 0 w2 less than or equal to again than or equal. And your last cost coefficient in the problem, final problem, that is nothing but, and we have w1 that will remain the same. Okay. Now, yes, suppose that the problem is like this. Our final LPP was like this. Minimization of LPP. So 3x1 minus 2x2 plus 4x, like this. Okay. Earlier it was maximization problems, all the primal LPP, but you have to find out the dual of this primal. So how to find out is, you have to first of all you should know how this canonical form, uh, this canonical form of primal problem is got changed in the case of minimization Z. In that case, all this less than or equal to becomes greater than or equal. So our canonical form will be, right, this primal problem is minimize Z is equal. So this less than or equal to becomes greater than greater than. Okay, so only that difference, and the rest of the form is same. Okay, so we have a problem like this. We will solve it so that you will understand better. So minimize Z subject to the constraints. We have 3x1 plus 5x2 plus 4x3 greater than or equal to 7. Then 6x1 plus x2 plus 3x3 greater than or equal to Then we have 7x1 minus 2x2 x3 less than or equal to 10. And also we have 2 less than or equal to x1 minus 2x1 plus 5x greater than or equal to 3. Not finished yet. Other 4x1 plus 7x 7x2 2x3 greater than or equal to x1 x2 x3 greater than or equal to 7. Right. So we have 1, 2, 3, 4, 5, 6. 6, 7, maybe. So, 1, 5, 6, and 6. Yes. So there are 6 number of constraints. Right. So B1, B2, B3, etc. B6. B1, B2, B3, etc. B6. So you have to define W1, W2. That means 6 number of W's. So 6 number of new variables or decision variables how to define in per dual. And right, and if you observe this problem, we can find that this is not in canonical form. Why? Because all for minimization problem, all must be greater than or equal. But in this case, here this 7x1 minus this linear inequality equation is less than or equal. So you have to make it greater than or equal to by multiplying by minus 1. Okay. Then the rest of the things are same. Rest of the things are same, and that means you should form a matrix. A is equal to some matrix. You can write 6. Yes, 6. We have 1, 3, 7. Not 7. Actually, this is by minus 1, so it's 7. So plus, and this becomes greater than or equal to right. So it will be minus 7, right? 7. Then 2, 2, then 1. Right. So like that you will get the matrix. Yes. Then you have x1 0 1 0. Then 1 we have 2 we have 5. Right. So you have the rows. Then in the dual this row becomes column, and this column you can write it as row. So 6 minus 7 0 1, and in between you have W1 W1 W. So right. Okay, my matrix A is wrong. Actually, it is not. 613 is second row. Before that, we have 3, 3, 5, and right. So it will be 3, 3W1, right? 3W1 plus 6W2 minus 7W3 plus 0W4 plus W5 plus W5 plus uh, plus W5 plus 4W6 equal to 0. Right. 0. Here we have 4 also. I got 4, 7. This row also I didn't write it. So this is our text, right? Yes, like that you can form the dual of LPP.